Now Einstein considers at this point probabilities, and he rewrites the entropy of one system S1 as a function phi1 of a probability W1, and S2, which is the entropy of a second system, as equal to phi2 W2. So the total entropy of the overall system, composed of the two subsystems 1 and 2, this entropy will be S1 plus S2. This will be a function phi of W, but W is equal to W1 times W2 because we have to multiply all the possible combinations of the two subsystems in order to obtain all the possible combinations for the overall system. So phi of W1 times W2 must be equal to phi1 of W1 plus phi2 of W2, like this. But now you can see that this equation is actually satisfied by logarithms. Natural logarithms, for example, can satisfy this equation. So phi1 of W1 is of the form constant times the natural log of W1 plus some other constant. Phi2 of W2 will be some constant, the same constant times the natural log of W2 plus constant, whereas phi of W will be the same constant times the natural log of W plus constant, like this. The quantity C, this constant here, is therefore a universal constant. The kinetic theory of gases shows its value to be R over N. Einstein proves it in other papers, and R over N is the Boltzmann constant, K. So we can rewrite S minus S0 in general as R over N, natural log of W, which is a probability. Einstein already showed it in other papers on thermodynamics. Now Einstein considers the following special case. He considers a number n, lowercase n, of movable points, which are molecules, for example, and these molecules are confined in a space, in a volume, V0. He thinks, for example, of an ideal gas, and he also thinks that, he imagines that these n movable points transfer into a volume V, starting from the volume V0. This is the initial volume, then all these particles, all these molecules go to the volume V. They are enclosed by the volume V. Now, the final state will possess a different entropy, which is called S. The starting entropy is called S0. And in this condition, we wish to evaluate W, this kind of probability. How large is the probability that a randomly chosen instant of time, all n movable points in a given volume V0 will be found by chance in the volume V? Well, this probability is quite easy to calculate. We simply have to take the ratio between V and V0, which represents the probability that one particle goes into the volume V. But if we want n particles, then we have to raise this to the power n, where of course V is less than V0. It's a smaller volume. Therefore, if we put this expression there, we get S minus S0 equal to R n over n natural log of V over V0, like this. So, from the theory of gases, we obtain something like this, but also remember that considering radiation, we obtained something like this. That's important. And Einstein then rewrites this formula like this: S minus S0 equal to R over N natural log of V over V0 N over R E over beta nu. So Einstein was just using the properties of logarithms here. There is nothing really major. But then, if we compare this expression with this one here, and we can also rewrite it as R over N natural log V over V0 to the power N, like this, Well, we see that the probability W for radiation in this case, so if monochromatic radiation of frequency nu and energy E is enclosed by reflecting walls in a volume V0, the probability that the total radiation energy will be found in a volume V at any randomly chosen instant is V over V0 to the power n over r, E over beta nu. So it's as if this exponent here is replacing this lowercase n here. So it plays the same role. This is important. And from this, Einstein concludes that monochromatic radiation of low density within the range of validity of Wien's radiation formula. Remember that. So when there is low density, it means that the frequency is very high, because if you remember, according to Wien's law, this exponential is small because nu is very large. So rho is small. And this monochromatic radiation behaves thermodynamically as though it consisted of a number of independent energy quanta of this magnitude. So R beta nu over n. Here we have the total energy of that monochromatic radiation, and if we divide the total energy by the energy of a single quanta, which we can call, for example, E0, we are going to get the number of quanta. So E0 is exactly this parameter here. So this is E0, the energy of a single quanta. Then Einstein wishes to compare the average magnitude of the energy quanta of the black body radiation with the average translational kinetic energy of a molecule at the same temperature. The latter, meaning the average translational kinetic energy of a molecule at the same temperature, is 3/2 R over n times T. We have already seen this formula, but according to Wien's formula, we have to take an average, right? So in principle, we have to integrate from 0 to infinity. Here we have the distribution, e to the minus beta nu over T. The nu, we also have alpha nu cubed, and we also have to divide by integral from 0 to infinity e to the minus beta nu over T d nu. We have alpha nu cubed, and in principle here we should put the energy of a single quanta, which is R beta nu over n. But this is not the way that Einstein calculates this average, because if you think about it, we are integrating from 0 to infinity, but this distribution is correct when nu is very large. So when nu is very large, this will become very small, and therefore we are not calculating the average appropriately, because this quantity will be averaged over the small frequencies, since, as I said, this factor will become very small. So the way that Einstein calculates this average is by considering the inverse of the energy, and he puts the inverse here, n over r beta nu. By doing so, is going to average over the higher frequencies, because in this case, when we integrate this term over small frequencies, for small frequencies this will be very large, and therefore we are going to get a better estimation of the average. And if this calculation is performed, we obtain 3RT over n.